Welcome back, chat. Thanks for the sub. Appreciate it. I don't even know. What do people give on Twitch? They say thank you for something.
Gifted subs.
Gifted subs? Welcome back, chat. Thanks for the gifted sub. I don't know if that's how it works. Okay. Quick check. Yes, thumbs up. You gave me the, like you found these numbers, or thumbs down, you didn't. Okay, so we're about halfway through. Quick check. For those of you that gave me this, why? You forgot?
It was part of my homework and I thought I did it already.
Okay. This is a hard one to answer, but just in case, it's possible that somebody in here just didn't know how to do it. Yeah? Like, that's okay. Let's sort it out. Okay. Here we are. We could get nice numbers here, and we will here shortly. I'm going to leave a blank space for just a moment, and I'm feeling kind of red today. Force of Chrissy. Here we go. What's the magnitude of Chrissy's force? 17.7 newtons, right? Can you tell me the direction at which Chrissy is pulling from the x-axis? Positive. So from the x-axis, let me be more specific. Which angle from the positive x-axis is Chrissy pulling at? Holy quiet. Yes, though, I think. Did you say 55 degrees? Love it. So check it out. On your calculators, do me a favor. I'm going to make that side of the room get me Afua's numbers. Right side of the room, I guess your left. I want you guys to find me Chrissy's numbers. But it's as simple as 17.7 times the cosine of what angle? 55 degrees. Make sure your calculator's in degrees. And then 17.7 times the sine of 55 degrees. And I do not have these numbers in front of me, but I will trust you guys to do so. So here we go. I'll switch back to black for there. I suppose I'll fact check you. Which one are you guys doing? You're doing Afua? You guys doing Chrissy? You guys do Afua. Some of you already have it, but let's just verify. And it seems silly, but you should. Everybody should grab a calculator if there's one on your desk. You get negative 10.2 right there. And then this one's going to be uglier. 17.67. And really it should be 17.6669. Cool. Okay. For this side, what did you guys come up with? You did 17.7. Where's my cursor? Weird. 17.7 times the cosine of 55 degrees. A little bit more confidence. It's 10.2 again? 10.1523. Okay, and the x, or sorry, the y?
There's like
What's after the 8?
9.
And what's after the 9?
9.
Okay. Boom. All right. I need confirmation. Yes, I can get these numbers. No, I can't. Follow-up confirmation. I understand where these numbers came from. Cool. All right. So we have Afua's force. We have Chrissy's force. I don't remember what we're after because I covered it up with a picture. We're just looking for, the initial force on the box. So we have, at this point, a few different forces that we're dealing with. This last one, we know that gravity is also at work, yeah? I'm just going to call this one F sub G. I think that's like the most natural choice. I'm going to use this darker orange because it's easier to see, I think. FG, everybody cool with that? Now, there's a couple ways that we can get FG. I already know it's magnitude, yeah? Can you guys tell me, and that's a terrible way to ask a question, quietly discuss, about 30 seconds, if you need it. I want you to do that vector, FG, and we're just going to get all three of them. I want you to write this vector in component form for the gravity. Cool. 30 seconds. I'm a pause. Doing anything crazy, but I want you to do me a quick favor. In this picture, and I'll look here, you do not have to write this, and I don't have a good alliteration for that yet. But check it out. That's the positive x-axis, right? What's this angle here? Do me a favor real quick. Type 31.36 times the cosine of 270 and 31.36 times the sine of 270, which is the same thing we did here, but we don't have to do anything crazy with it. If you didn't quite catch it, I'm asking you to do 31.36 cos 270, and I'll move or delete that. 31.36 times the sine of 270. Now, when it's a nice quadrantal angle like that, which just means like on one of the quadrants, there's like no thought that has to go into it. But did you just get 0 and 31.36 again? Oh man, super convenient. 0 and 31.36. Okay. We now have Afua's force. Check. We have Chrissy's force. Check. And we have the force due to gravity. These are all the forces at work in this problem, right? And we're asked to determine the initial components of this. That's like asking you to find a special vector that you get when you do what with these three? When you add them up. So, check it out. And let's just decide if I want to word this. Find the x and y components of the initial net force on the box. Cool. Sweet. I want you to add up these vectors. I want you to find the net force of this problem by taking the force of Afua plus the force that Chrissy exerts plus the force that gravity exerts. With the understanding that I have a little typo here. What direction does gravity pull this? Downward. Cool. Add up those vectors for me.
Is that negative 31.36?
It is.
Negative 31.36. Just write down.
Okay, up on the board what I've written without writing down any of the ugly numbers, and not necessary, but this is what my head is thinking. It's what I hope you're doing. Does every one of those vectors we just found have an x component? Now, I don't really want to write these terribly ugly numbers again, but I trust your calculators because we have them all written in the similar spots. How do you combine vectors in this form? If I have all these x's and y's, how do I make them one vector? Add the x's and then add the y's, right? So here's all my x's and all my y's. I am using a little bit different notation. What do you think this represents? Don't be shy. It's okay to be wrong. What's A represent in our problem? So this is the force of Afua in which direction? X. Like this is just me not wanting to write all those big numbers. I don't know if it's any faster in hindsight. But let's do a little bit of math. Can you guys do negative 10.2 plus 10.1523 plus 0? And is that what you did? Cool. I have no idea what it is, but you can hook it up.
Well, if you
It's not quite 0.
is 10.
If we round here, it'd be 0, right? Do you want to say it's 0? Like, it's up to you how far you want to round. What do you guys think? If this is 10.2 and that's only 3 sig figs, how many sig figs should we probably use? 3. I'm cool with 0. How about the y direction? If you do 17.66 plus this. I don't know the number. 0.8069?
Yeah.
Okay? So let's look back at the actual question. This is our ending vector. Who wins, Afua and Chrissy or the Earth? Hey, Afua and Chrissy win because in the end they are pushing, or pulling rather in this situation, upward with what force? Yeah, check it out. They win if all I mass, and I can't see it because I covered that up, but check it out. Afua and Chrissy pull the box upward with a net force, and I'm just going to write F net of, it's straight up, yeah? No left, no right. How many newtons? .8069, or I'm okay, like once we get here, if you want to start rounding, I don't mind. I will be pretty casual with how hardcore I am on those. Cool. Straight up. These problems, they're weird to get used to, but I cannot stress enough that using this component form and getting used to it is going to simplify every type of problem with vectors that you will ever do. The alternative to this is just playing the crazy geometry game, which is rough. Beyond that, your guys' favorite chapter from Algebra 2 is one of two, is my guess. It's either you absolutely loved factoring and graphing, quadratics and those things, because that's everybody's favorite thing. You probably also really, really enjoyed matrices. Cool. What's a matrix? So hard to explain maybe. Do you guys, can you get an image in your head of a matrix? If we wanted to, do you think it'd be possible that, man, we could and we don't have to here, but I'm just showing you how different ways that math shows up. Could we write this as a 2x2 matrix like this? Like this force right here. Could we write it as, hey, look, it has an x and a y like this? And then we start getting matrices that we can start to move around. This is linear algebra is what this is called. We're not doing any of the theory of it, but same ideas wrapped around math in a bunch of different ways. Yay, nay, thoughts on this problem? Mean comments for me? Polite comments for me? Compliments?
Bad job, Holloway.
Terrible job, I feel it, you know, in here. Cool. Okay, let's check the rest of the homework. Does this feel better now than it did yesterday, or does this feel just as bad? Okay, the good news for you is that we get a bunch more practice because we could keep doing these. All right, so which ones did we actually do for homework then, 8 through 16? Cool. There's answers in here somewhere. If I read the wrong answer, because I don't do all your problems just so you know, I found one on my answer stuff that is wrong. So, like, if I read a wrong answer and you're, like, confident that you did it right, call me out. We'll look at it. But check it out. Number 8 we talked about. Number 7 we did yesterday, yeah? Did we? Yeah, we did. Cool. Where am I looking?
We didn't have 7.
Why am I looking at 7? We did number 9 yesterday. What did we get for number 9, just out of curiosity? Gosh, I'm proud of that answer. Number 10 we just did. Number 11. Find the components of vector m that they show you. Did you use SOHCAHTOA? Hey, cool. When you take 5 times the cosine of 37 on number 11, you're probably going to get 4. And when you take 5 times the sine of 37, you get about 3. Cool. Makes sense. Pythagorean triples, a 3, 4, 5 right triangle exists. Once you got one of them, you didn't need the other one. You can still do it. 3, 4, 5. Awesome. Number 12. Find the components of k and l. Weird. K is negative 4 comma 0, so 4 to the left, 0 up or down. L is 6 comma 0, 6 to the right, 0 up or down. Cool. Quick check real quick. Give me a thumbs up. Everybody, like straight up, give me a thumbs up. How far back does your thumb go? Anybody have this weird mutation like me? Anybody got a hitchhiker's thumb? Hey, you and me both do. Other random thing that I realized that some of my classes can't do. Hands together. Okay, I want you to make your fingers do a wave while they're still connected. So if you struggle with it, it's going to do this, and people just make, hey, you can do it. Can everybody do a wave? Riley can do it. Kind of. You guys are much better about it than my fisheries class was. A lot of people just do this. Which, yeah, if you can't do it, that makes sense. 13. Find the sum of the three vectors shown in figure 9. Oofda. Hey, I have an answer. But so do you. What's the length of the resultant? Or did you just give me a component form of a resultant? 3.6, and this is number 13. We should look at that one. We need to look real quick. I don't like 3.6, I don't think. This claims that this is number 13, right? 6.7 is what it claims. Let's check it. There's room somewhere to work here. Cool. All right, so I'm just going to write these three vectors just as they showed up. We decided, and let me know if you disagree, from the previous problems, vector k, we said was negative 4 comma 0. Vector L was 6, 0. And I do not remember what vector M was, but it was 3, 4, 5, right? So it was 3, 4. Everybody cool with that? Now, I've written these super nicely. Not real numbers. The vector R, my resultant. Negative 4 plus 6 plus 3. 5. 0 plus 0 plus 4. Okay. So there's the actual vector, right? Now, when they say find the resultant, and I don't love that language, find the sum of the three vectors shown, do you have this answer? What did you do, out of curiosity? Okay, so like you physically drew it? Okay, if you draw it, that's all right, but check it out. It doesn't matter where we start because vector addition is commutative. And I have a nice scale. Is that negative 4? Everybody's cool with that? And then from there, I'm going to add onto it L, which says I move here and I go 6 to the right. So here it is. That puts me at 2 positive. That puts me at 2 positive.
Is this 14 or
13.
13?
Yep, so it says add those vectors from the previous problem. And then I add M, which is 3, 4. So I'll add M here and check it out. Here's 3 to the right and then 4 up. Is this what your picture looks like, Rafa? What does your picture look like? Okay, so, and that's all right. Maybe you just didn't add all of them, is what it looks like to me. Okay, now if we look at this, notice what just happened. The actual component vector, or the resultant, is this one, yeah? From start to very end. Notice, if this is the origin, what point is this? Hey, look at that. You can do it graphically, or way faster, we can do it this way. If I'd done L plus K plus M, would I have wound up any different? I don't think so. Let's say this is my vector instead. If I do L and I go to, hey, 6, 0, and then I add, and I'm just going to go 3, 4 instead. Here's 3 more. And is that 3? And 4 up. And now I go 4 left. Where do I add when I go in this direction? Or where do I end up? Hey, cool. It's the same. Doesn't matter which direction you go in. As long as you go tip to tail, you always wind up at the same spot. Now, if this was the answer you gave me, I'm okay with it. But they're asking for a few more things. What does this represent? It's a magnitude, and we can all do this super easy. It's a square root of, and if I look at just this triangle with the dashes, just this one, I know that this is 5, and this is 4, right? How do you find the third side? Oh, my Pythagorean, what's 5 squared? Plus, what's 4 squared? What's 25 plus 16? That feels like a prime number. Boom, 6 point something. I don't know what it is. 6.7 is my, not guess, I'm looking at the answer. 6.7. What if I want to know theta for this resultant R? if I have this triangle, I know 4 and 5. Here's my angle theta right here. How do you find it? I'm calling somebody random about 15 seconds. Talk it out. Might be you. I'll be number 13. In 5, 4. Don't care if you're wrong or not, but I want an answer. Number 3. I don't know who it is. Is it you, Huggins? Follow-up question. Is your phone in your pocket? You should put it back there in a minute. But how do we get theta? Which trig function could I possibly use for that right triangle that I've highlighted? Give me the 3 trig functions real quick.
Sine, cosine, tangent.
Okay, so we didn't really go into the story, so this one always feels weird in here, I imagine. That Lakota chief that I mentioned briefly?
The what?
The Lakota chief? Gosh, I should have told you guys that big long story too, but it takes like a lot of time. SOHCAHTOA is the Lakota chief that I'm always referencing, because when I teach this in geometry, I tell them a big long story. That's just a lie. What of those sides does represented with respect to this angle theta? 4 is the what side?
The opposite.
Opposite, and this is the,
Adjacent.
which trig function requires opposite and adjacent?
Tangent.
So, tangent, TOA. If you need to write this on top of every assignment when we're doing trig stuff, I would encourage it. SOHCAHTOA. Opposite and adjacent is tangent. Now, there's a shortcut. You can do it this way. Tangent of theta is 4/5. Everybody agree? How do you undo a tangent? The inverse, or the arctan. So I'll do it to the left side to get theta equals the arctangent of 4/5. I don't know what that is, but your calculator will. And let's see, just thinking about it. 27? It's not 27? Lame. 28.38. Jeez. 38 point what? Holy cow, your book is wrong again. I'm confident with us. Like, I know this is right. I can tell it's right. We just did it. Your book is wrong again. Or my answers are wrong again. Your book's answers for me. I don't know how to word it. Cool. All right. Doable? Sweet. 14. How does it end up? K minus L? Now, if we look at it in component form, it's super easy, I think. If you took K minus L, what's negative 4 minus 6? Because I see these right here. We're still talking about these same vectors. This minus this. Negative 10 and 0, right? Check it out. Negative 10. We got it. Was it L minus K? Subtract K from L. So it's L minus K. So we're just going to switch it around. What's 6 minus negative 4? Hey, look at that. We get 10. That's it. That's our answer. All right, 15. I unintentionally did already by showing that vector addition is commutative. Didn't even look at the problem. That's my bad. You should have a picture like those up there where we're combining them, where it just shows, hey, which one works the same. Ooh. 15B might have been a struggle, yeah? How did you try to approach it? Are we in a pure math class? We're going to skip it for now. If anybody has a good answer, I'll read your answers. I'd like to see what they are if it was answered. And then finally, is the distance you walk equal to the magnitude of your displacement? Give an example that supports it. What do you think, Delilah? The distance I walk is the same as displacement. Love that answer. It can be. If you don't change directions, it will be. However, the second you make any sort of change in direction, we're going to get a bigger number. Cool. I'll take them. I don't want to, but I will. And as you're getting them ready, I'm going to put this Euler disk to start. Can everybody see it if I put it right here, or is it better on the counter? Or, yeah, we're just doing it here. Okay, you guys have seen, obviously you've seen coins spin, right? How long does a coin spin? That's a weird question, but like guess if you had to. If you spun a quarter, how long is it going to spin for? You do really well. Say it again. 5 seconds.
45 seconds.
45. I don't know. Maybe. All right, we're starting. Somebody look at the clock for me. We're starting at 20 seconds. Don't you fall. Minus 0 with 15? Cool. 15 seconds. That was a pretty good spin. I'm going to keep collecting stuff. I'll come today. Everybody see this? Or you can stand up if you can't. Okay, this one I don't have to worry about leaving because it's on a little slightly convex surface, which just means the surface is kind of curved like this. Cool. I'm going to spin it. Well, it's doing about the same thing as a coin, right? That's lame. I'll start timing now. We're at 5 seconds. Hey, you stay still. So how's your morning? 30 seconds right now, and I started about 10 seconds late. Oh, Sean has it. 10-2. It's sitting on that ruler is the issue. Ah, that was lame. I didn't realize it was on level. We'll do it right this time. And let's see. Did I can grab your snap? I don't have to be recording the blink noise. Friction. Cool. We're not gonna have homework. Not today anyway. But let's jump in. We are looking at 5.2. And over the next few days, and hopefully with the lab, I gotta talk to Mr. Jim to make sure everything's all right with that. We gonna talk about frictional forces. And I lied, I'm just gonna call it friction. Okay. Hate doing it because it feels redundant. But right off the bat, you guys all know what friction is, yeah? Cool. I'm going to give you like 30 seconds. Come up with your own definition. What is friction? And that's where we're going to start with a vocab right off the bat. What is friction? Without just reading your textbook is the answer that I'm looking for, or the question I'm asking. Weird. Rafa, you said a word right off the bat that I really liked. It's a surface force. Now, check it out. If I don't have it, but if this calculator were magic and could hover in the air and I tried to push it, would I have friction? So I had to be touching it, right? As in contrast with a field force like gravity and magnetism and stuff, which can act at a distance without touching it, friction has to touch, yeah? Which means it's a what force? Love it. Excuse me, somebody said contact. We're just going to say friction is a contact force. It is a contact force between an object or between two objects that resists, we're going to say motion. Now, there's a few additional little pieces that we can make about this. If I'm pushing it forward, like my applied force is forward, friction pushes what direction? Backward, right? It goes the opposite direction. So I'm just going to say it resists motion. And then we're going to make a couple comments. First off, the word friction and this subscripts are going to be like super important. It's tedious, but just commit to it. We're going to say that the force of friction, F sub F, capital for force, lowercase for friction, is opposite the direction of motion. Or I'm going to say opposite direction of applied force. That's a better way to word it. Okay. Beyond that, we get a couple different flavors of this. You guys told me a second ago if we had to push a car, when's it hardest? At the beginning. Now, easier when it gets moving. And with tires, same thing applies with whether you have tires or not. But we get two different types. So, looking at this, two types of friction. And remember, there are more than just the two. There's that rolling friction, but we don't cover rolling friction in here. One could argue that drag force is just friction in the air. Seems reasonable. Cool. You guys, let's look at, typically when I think of pushing something, it's from rest until it moves. So we're going to start with the beginning of no movement. So here we go. First off, static friction. I'm going to make this a vocab. Static friction. Okay, and then what I'm going to do is I'm going to introduce the shorthand for this right off the bat right here. Static friction, when we write it, it is a force, and it's friction, which means I'm going to use which subscript first? Force of friction is F sub F. So here it is. And if it's static, we're going to use S. The force of friction that's static. That's what this represents. So we'll just say that this guy is the oppositional force. Oppositional force. Before an object moves. Now there's some weird things about this. Turns out it's not constant, which is a weird idea. So check it out. I'm going to use this calculator. You guys can push on stuff on your desk. I'm just going to make up numbers, okay? I'm barely pushing it, and it's not moving. So right now, my forces, if it's not accelerating, it's not moving, the forces should be balanced, right? If I'm pushing with 1 Newton right now, how hard is friction pushing back against me? 1 Newton, right? Okay, I'm going to push a little bit harder, and it's still not moving. I'm now pushing with 2 Newtons of force. All of a sudden, the static friction is how strong? 2 Newtons, and it keeps changing, right? The value and how strong that friction pushes is dependent on how hard I push against it. Means it doesn't exist without me. Right now, there's no static friction going on because there's no applied force. It doesn't have to fight anything. If it still existed, and if we just stick with the same direction, if I'm pushing that way, friction pushes that way, yeah? If I don't push it and friction still existed, there'd be one force pushing that way, and my calculator seemingly would just start moving itself, which obviously doesn't happen. As we deal with this, I'm going to make that comment as concise as possible. It is dependent on agent of, and then instead of writing applied force, I'm going to say F applied. And the subscripts, as much as it sucks, it is so much nicer and easier to keep track if you do the tedious subscript stuff. Because we wind up getting a bunch of forces at work. Label them clearly. It will save you. Cool. Now, in contrast with this, something, if you overcome static friction, you push harder than friction can. What starts happening to the object you're pushing? It starts to move. And static is the fancy word that says, hey, we don't move. What's a fancy word for we do move or stuff is moving? Start with a K. Kinetic. So check it out. We also get this idea of kinetic friction. All right, it's a huge stretch, but hook it up. The shorthand for kinetic friction. Probably an F because it's a force. What should my subscripts be? F, good. K for kinetic. Hate that K. Cool. We have it. How do you think that we would explain this? Static is oppositional before an object moves. What's kinetic friction? Opposition while it moves. Cool. Can I just say that and be less wordy? Opposition while moving? Because we just wrote the other one above it. Okay. Now, couple different things that go on with this, and I just want to consider a couple different situations. So I am going to have 3 different pieces, and I usually draw free body diagrams. We're going to draw this guy pushing. So this guy's going to be pushing a box. Cool. And then I get to cheat with this because, I don't know, I have this. What? Cool. I want 3 scenarios. You can just use a dot if you want. So check it out. In this first one, I'm going to say that v equals 0. I'll move it over. The velocity is 0 meters per second. That's a fancy way of saying what? It's not moving. Okay, cool. So hypothetically, and remember free body diagrams, and I'm going to draw the free body diagram below it as well. All my forces come from that dot. So hypothetically, I'm pushing at, I don't know, I have no idea how heavy this box is. Let's say I'm pushing at 50 newtons of force. If it's not moving, there must be something fighting me, yeah? Cool. So this is my applied force. In red is what? Force of static friction. So I will do a better job of this. I'm going to say the force of friction that's static, what would it equal? You're so close. Less close. Negative 50 is what I need. Now the magnitude, you're right, totally, just so you know, like obviously it's 50, but it's going the opposite direction. Okay, in this situation, let's say we add a couple more things. I have, let's check it out. Velocity is greater than 0, but acceleration is 0. Cool, so I'm going to move up on this and let's check it. Let's say all of a sudden, my dot diagram below, I have the force that we apply. So I'm going to say F. You guys want to agree to shorthand app for applied? And I will write so much bigger because my small writing gets smaller when I use tiny subscripts. F applied. Let's say it's 70 newtons. Now, because it's not accelerating, what's the net force? 0, which means there's something else going on here. What force did I just highlight in red? It's moving, right? Because I see velocity is greater than 0. This is the force of friction that's kinetic. And if we're not accelerating, what must it be? So the net force, Riley, you're absolutely right, is 0. But because I need the net force to be 0, that must be there. Okay, last one. Let's say on this guy we have velocity is positive and acceleration is positive. And I could have done, I should have changed the number. Do you guys have room to sneak something in? Can you put a 1 in front of this number? Do you have room on yours to make this 150 newtons and 150 newtons instead over here? I made on that first one, instead of 50 newtons, I made it 150. Why did I change it? Harder to start moving or keep moving? Start. I wanted that to be bigger for that. We will look at this last situation tomorrow. I would encourage, it'll take like 5 seconds. Let's say that I'm now pushing with 80 newtons. That's my applied force. Come up with any number that's realistic for my force of kinetic friction. And I'll see you cool cats and kittens tomorrow.